Tonight, we're going to dismantle an image that has been sitting quietly inside your mind since you were a child. You don't think about it often. You may not even know it's there. But the moment I describe it, you'll see it. Two glowing spirals, one labeled Milky Way, the other labeled Andromeda. Between them, a black line, an arrow, a number, 2.5 million light years. And between those two galaxies, nothing. Just darkness, just space. Just the long, cold, empty distance that you have been told for your entire life separates us from the nearest great galaxy in the universe. That image is a lie, not a deliberate lie, not a malicious one, but a lie of omission so vast, so quiet, so old, that almost no one ever questions it. Because the truth of what fills that supposed emptiness, the truth of what is actually drifting, glowing, flowing, pulling and waiting between the Milky Way and Andromeda, is so strange, and so much larger than the picture in your head that astronomers themselves are still adjusting to it. So here is the question, the one that will orbit everything we say tonight, the one that, if you let it, will follow you out of this video and into the quiet hours after and maybe into your dreams. What if there is no between? What if the gap you've been told about, the dark gulf, the empty void, the lonely distance, is not a gap at all? What if it is full? What if it has always been full? What if the Milky Way and Andromeda are not two separate islands floating in a sea of nothing, but two bright places inside a single enormous structure? One that you, sitting here right now, are already a part of. That's where we're going tonight. But to get there, we are going to take our time. We are going to start small, with the familiar diagram you've seen 1,000 times, and we are going to slowly, patiently pull it apart. We will begin with the textbook lie, the diagram itself, where it came from, and why almost everyone on Earth carries the same wrong picture of our cosmic neighborhood. Then, we will follow the first crack in that picture. The discovery, only a few years ago, of stars wandering more than 1 million light years from the Milky Way's core, nearly halfway to Andromeda, drifting in the dark, claimed by no galaxy, contested by both. Stars that should not be where they are. Stars that, until very recently, no one even knew existed. We will travel deeper. We will visit the hidden cities of the in-between, the dwarf galaxies. Some you may have heard of, like Triangulum. Most you have not. Galaxies with names like Cassiopeia dwarf, Pegasus dwarf, Andromeda 18, Pisces 7, Pegasus 7, Andromeda 36. Tiny, faint, ancient. Some discovered only this year. Some still being argued over. All of them living in the supposed emptiness, all of them quietly orbiting, drifting, and being slowly torn apart. And then we will go thinner still. We will descend into the gas. There is a river of hydrogen connecting Andromeda to its companion Triangulum, a bridge of cold neutral gas stretched across the dark, longer than the diameter of the Milky Way itself. There are streams of torn gas trailing behind small galaxies that have been falling toward us for billions of years. There are clouds raining down onto our own galaxy at this very moment. And around each of these galaxies, there is a vast envelope of ionized gas, an invisible halo, reaching out so far that, and listen carefully here, Andromeda's halo and the Milky Way's halo may already be touching. They may already have been touching for a very long time. And underneath that, thinner still, hotter still, we will find the warm-hot intergalactic medium, a gas so diffuse you could fly through it and feel nothing. A gas so faint we could barely see it until the last few years. A gas at temperatures of 1 million, 10 million degrees. A gas that, by the best current estimates, may contain more than a third of all the ordinary matter in the universe, more than every star, every planet, every moon, every comet, every human, every atom you have ever touched or breathed or eaten combined. And underneath even that, we will find the architecture that holds everything in place. The dark matter, a vast, invisible sheet of it, stretching tens of millions of light years across, with our entire local group resting on it like a leaf on still water. a sheet so wide and so structured that the Milky Way and Andromeda are not really two galaxies inside it. They are two bright peaks rising from the same hidden landscape. And then at the very end, we will turn to the question that everyone asks first but that we have saved for last. Will they collide? For more than a decade, the answer was yes. Certain. Inevitable. In 4.5 billion years, a great smash-up. A new galaxy. A name that almost feels like a joke. Milkomeda. But in 2025, that certainty was undone. A new study, using the best data we have ever had, ran 100,000 simulations. And what it found has changed the future of our galaxy from a near certainty into something closer to a coin flip. We will talk about that flip. We will talk about what it means. And we will talk about what it tells us, not about Andromeda, but about ourselves. Before we go any further, though, I want to ask you one small thing. If this kind of slow, deep exploration of the cosmos is something you find meaningful, if you've been looking for a place to come back to on nights like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me, and then we'll begin properly. Now, settle in, let your shoulders drop, let your eyes close if that's how you prefer to listen. You don't need to follow a diagram. You don't need to remember a number. Everything you need to know, I will say in your ear as we go, because there is so much waiting for us between the Milky Way and Andromeda, so much more than you were ever told. And by the time we are done, somewhere in the small, quiet hours, the diagram in your head will not look the same again. Before we move on, I want to hear something from you. When you were a child, the very first time someone told you that there were other galaxies, what did you picture? Did you see two bright spirals floating in pure black? Did you imagine ships could one day sail across the gap? Did the gap feel lonely to you, or did it feel beautiful? Leave a comment and tell me. I genuinely want to know what image lived in your head, because tonight we are going to slowly, gently replace it with something far stranger, and I think far more beautiful. And the place we are going to start is where every wrong picture of the cosmos always starts. Not with a mystery, not with a discovery, not with a telescope, but with a single tidy diagram drawn for a textbook decades ago by someone who only had room on the page for two galaxies and a number. A diagram so neat, so familiar, so comfortable, that almost no one has ever stopped to question what it leaves out. So let us walk back to that diagram now, the one in your mind, the one in your old school book, the one in every documentary you have ever half-watched, and let us look at it again, slowly, carefully, for the first time. Because before we can understand what is really there, we have to understand what we were taught was not. Close your eyes if you haven't already and let me draw the picture for you. The one we are about to take apart. You are looking at a page. It might be a page from a school book. It might be a slide from a classroom projector. It might be a thumbnail you scrolled past on your phone last week. But the image is the same, everywhere it appears. On the left side of the page there is a spiral galaxy. It is glowing. It has graceful, sweeping arms, a bright golden center, a label underneath that reads simply Milky Way. On the right side of the page there is another spiral galaxy, slightly larger, slightly tilted. Also glowing, also golden, also beautiful. A label underneath that reads Andromeda. And between them, between those two bright, busy, intricate worlds, there is nothing. A black band, a line, an arrow, and a number. 2.5 million light years. Sometimes it is written in scientific notation. Sometimes there is a small inset showing the local group. Sometimes there is a dotted line indicating the path of an eventual collision. But the essential picture, the picture that everyone carries, is this. Two galaxies, one number, and in between a darkness so complete that it requires no description. That is the diagram. That is the lie. And to understand why it is a lie, we have to understand why it exists. Because the picture in your head did not come from nowhere. It did not arise spontaneously in your childhood imagination. It was placed there, very carefully, by a chain of teachers, illustrators, science writers, and animators, every one of them trying to communicate something true about the universe, and every one of them in the process being forced to leave almost everything out. The story really begins 100 years ago. In 1923, a man named Edwin Hubble pointed the largest telescope in the world, at that time, at a faint smudge in the constellation Andromeda. For centuries, people had argued about that smudge. Was it a nebula inside our own Milky Way? Was it a cloud of gas slowly collapsing into stars? Or was it something else, something farther, something stranger? Hubble found a single, faint, pulsing star inside the smudge, a variable star, the kind whose brightness can be used as a yardstick. And when he measured it, he realized, with a quiet shock that probably did not show on his face, that the smudge was not inside our galaxy at all. It was an entirely separate galaxy, almost a million light-years away, the Andromeda galaxy. And in that single moment, the universe became, somewhere between 1,000 and 100,000 times larger than anyone had imagined. Up until that night, the Milky Way had been the universe. Everything that existed, everyone believed, lived inside our own spiral. After that night, the Milky Way became one galaxy among many, and the philosopher Immanuel Kant, who had written more than a century earlier about the possibility of island universes, separate, self-contained worlds of stars, floating in the void, was suddenly, posthumously, vindicated. Kant's phrase took hold. It echoed through the early 20th century. Island universes, two words, two ideas, islands, separate, finite, surrounded by emptiness. Universes, each one complete in itself, each one self-sufficient, each one a world apart. And those two words, more than any others, are the reason the diagram in your head looks the way it does. Because if galaxies are islands, then by definition there must be a sea between them. A sea of nothing, a black ocean, a void. The diagram you grew up with is the visual translation of Kant's metaphor, repeated and repeated for 100 years, until almost no one remembered it was a metaphor at all. But here is what we have learned in the last 20 years, and especially in the last 5. Galaxies are not islands. The metaphor is broken. There is no sea between them. And the line on the diagram, that clean, neat 2.5 million light-year arrow, is not a fence. It is not a wall. It is not even really a distance in the way you have been picturing distance. It is the spine of something, the center of something, a region that is full of objects we are only just beginning to count. Let us start with that number itself. 2.5 million light-years. Pause on it for a moment, because the diagram makes it look small. The diagram makes it look like a short hop. 2 galaxies side by side on a page, but the number is, in fact, almost incomprehensible. Light, the fastest thing there is, takes 2.5 million years to cross that distance. 2.5 million years. When the photons currently arriving at your eye from Andromeda first set out on their journey, our ancestors were not yet our ancestors. They had not yet learned to control fire. They had not yet built a single tool you would recognize. The species we belong to, Homo sapiens, did not exist. Neanderthals did not exist. The continents were almost in the positions they are in now, but not quite. The light has been traveling quietly, patiently for that entire time, through everything we are about to describe, through the dwarf galaxies, through the rivers of hydrogen, through the dark matter halo, through the hot diffuse gas. And it has arrived, almost unchanged, to land on the retina of a person who picked up a phone tonight and looked for a video to fall asleep to. 2.5 million light-years is real. It is staggering. We are not going to pretend it is not. But the diagram makes a much stronger claim than just distance. The diagram claims that the distance is empty, that in those 2.5 million years of travel, the photon passes through almost nothing, And that is the part that turns out to be wrong. If you were to shrink the Milky Way down to the size of a dinner plate, about 11 inches across, the kind you might serve a meal on, then Andromeda would be another dinner plate, slightly larger, sitting about 13 feet away. And the diagram in your head insists that the space between those two plates is empty. Just air, just table, nothing else. But in reality, on that 13-foot table, you would find scattered crumbs all the way across. A small dinner plate of its own, the Triangulum galaxy, would be sitting about a foot away from Andromeda's plate. Dozens of tiny faint specks would surround each plate, like grains of pepper. Faint glowing mist would hover above and between the plates, sometimes pooling in long thin streams from one plate to the other. And the entire tabletop itself, the surface they all rest on, would be quietly humming with a structure none of your senses can detect, a slow, invisible gravitational fabric holding everything in place. You were not shown the crumbs. You were not shown the mist. You were not shown the streams. You were not shown the table. You were shown the plates and a label and a number, because that is all that fit on the page. This is what we mean when we say the diagram is a lie of omission. It is not that what it shows is false. The Milky Way is there. Andromeda is there. The distance is real. The labels are correct. But what it does not show, and what almost no diagram has ever shown, is the entire rest of the scene. The hidden inhabitants, the connecting tissue, the slow weather of gas and dust, the invisible scaffolding, the fact that the so-called void is, in truth, the most populated, most complicated, most carefully balanced region in our entire cosmic neighborhood. And here is something even stranger. The diagram has not just shaped what we picture, it has shaped what we feel. If you have ever looked up at a dark sky and felt even faintly that we are alone, that our galaxy is alone, that the distances between us and everything else are too great to ever be crossed, too vast to ever be meaningful, that feeling, that quiet ache of isolation was given to you by the diagram, by the two plates on the page, by the empty arrow, by Kant's island, repeated and repeated until it became part of how you see the night. We are going to take that feeling apart too, not by pretending the distances are small, they are not, but by showing you that distance in the way we have been picturing it is not what is really going on. Between the Milky Way and Andromeda, there is no empty stretch. There is no quiet gap. There is instead a region so dense with structure, so full of motion, so layered with hidden inhabitants, that astronomers now sometimes hesitate to call it a space between at all. Some of them have started to use a different word. They call it a region. They call it a domain. They call it, occasionally, a system. And in the most careful papers, they describe the Milky Way and Andromeda not as two galaxies separated by a void, but as two density peaks within a single continuous environment. Two bright places in one larger, dimmer, quietly active thing. That shift from two galaxies and a gap to one continuous environment with two bright places is the shift you and I are going to make together tonight. It is not a dramatic shift. It is not a sudden one. It will happen layer by layer, slowly, the way the eye adjusts to a dark room and begins to see what was there all along. So before we move on, I want you to picture the diagram one last time. Hold it in your mind. The two spirals, the black gap, the clean little number. Look at it carefully, memorize it, because we are about to begin pulling things out of that gap one at a time. And by the end of tonight, the diagram you started with will not just be incomplete. It will feel almost quaint, almost touching. The way an old map of the Earth feels when you find one in a drawer, and you see the parts the cartographer drew very carefully, and the parts that are simply blank, marked with the words, "Here perhaps there be something we have not yet found." Tonight, we are filling in those blank parts. And the first thing we are going to find waiting in the supposed emptiness, the first thing we are going to pull out of the dark, is something that, by every textbook rule, should not be there. something that for decades no one knew to look for, something that, when astronomers finally found it, made one of them say a single, careful sentence that has stayed with me ever since. He said, and I am paraphrasing only slightly, it challenges the notion that galaxies are islands at all. What he had found, what they had all found, was a star, and then another, and then another. Scattered, faint, ancient stars, drifting alone in the supposed void, more than 1 million light-years from any galactic center, almost halfway between the Milky Way and Andromeda, and nobody, until very recently, had any idea they were there. Before we go to them, I want to ask you something personal. Have you ever stood under a truly dark sky, far from any city, far from any porch light, and looked toward Andromeda with your naked eye? Most people never have. Most people, in fact, have never seen another galaxy at all. But if you have, if you remember a night on a road, on a mountain, on a beach, when someone pointed and said, "That faint smudge there, that is another galaxy," I want to know what it felt like. Did it feel close? Did it feel impossibly far? Did it feel lonely? Or did it feel, even for a moment, like something was looking back? Leave a comment and tell me. Because the answer you give, the feeling you had, is the feeling we are about to begin gently rewriting. And so let us go to those stars. Let us go to the first crack in the diagram. Let us go out, away from the Milky Way, past the edge that you were taught marked the end of our galaxy, into the supposed darkness, and let us meet the wanderers. For a long time, astronomers thought they knew where the Milky Way ended. There was a disk, the part that holds the sun and almost every star you can see with the naked eye. There was a bulge in the middle, glowing softly. There were the spiral arms, the ones every illustration draws so faithfully. And around all of it, there was something quieter, a great spherical cloud of older stars, called the halo. The halo was understood to extend, at most, about 100,000 light-years from the galactic center. Past that, astronomers believed there was simply nothing. Just the long, cold drop down to Andromeda, just the gap. This was the picture for most of the 20th century, and it fit the diagram, it fit Kant's metaphor, it fit the comfortable idea of two islands separated by an ocean. The Milky Way had an edge. Andromeda had an edge, and between those edges, an emptiness so absolute that astronomers rarely even bothered to model it. But over the last 15 years, and especially in the last 5, that picture has quietly fallen apart. It began with a kind of star called an RR Lyrae. These are old, faint, pulsing stars, the same kind of variable star that Edwin Hubble used, a century ago, to measure the distance to Andromeda for the first time. RR Lyrae stars are valuable to astronomers because they are predictable. Their brightness rises and falls on a clockwork rhythm. And if you know how bright a star truly is and you can measure how bright it appears, you can calculate, with great precision, exactly how far away it is. So they make excellent yardsticks. And they are ancient, many of them as old as the universe itself, which means they survive in the outer reaches of galaxies, in the dim and quiet places where younger, brighter stars cannot be born. A team of astronomers several years ago decided to use these old stars to map the true edge of the Milky Way's halo. Not the textbook edge, not the imagined edge, the real one. They scanned patiently across enormous swaths of sky, looking for these faint, ancient lights, at distances no one had ever properly searched before. Distances of 500,000 light-years, 600,000, 800,000, 1 million, and they found them. They found RR Lyrae stars more than 1 million light-years from the center of the Milky Way. Stars that, by every old textbook, should not have existed. Stars that were drifting alone in the supposed gap, far beyond where the Milky Way was thought to end. Stars that were not in any cluster, not in any dwarf galaxy, not in any clearly defined structure, just out there in the dark, glowing faintly. Let that distance sit with you for a moment. 1 million light-years from the center of the Milky Way. To put that in human terms, if the disk of our galaxy were the size of a city, with the sun somewhere out in the suburbs, then these RR Lyrae stars would not be in the next town. They would not be in the next region. They would be more than halfway to a different continent. And on the imaginary table we built in the last section, where the Milky Way was a dinner plate and Andromeda was another dinner plate 13 feet away, these stars are not on the plate. They are out on the tablecloth. Some of them are 5 or 6 feet from any plate at all. And one of the astronomers involved in this work, a man named Rajaguha Thakurta at the University of California, said something afterward that has stayed with me. He said that this work was redefining what counted as the outer limits of our galaxy. And then he said, very carefully, that the discovery challenged the notion that galaxies are islands with big, empty spaces between them. He even invoked Kant directly. The island universe metaphor, he said, was finally beginning to break, because here is the implication. If the Milky Way has stars at 1,000,000 light-years out, then the Milky Way's true halo is much, much larger than the textbook said. And if the Milky Way's halo is much larger, then Andromeda's halo, which is at least as large and probably larger, well, the math becomes uncomfortable very quickly. The distance between the two galaxies is 2.5 million light-years. If each one has a halo extending 1,000,000 light-years from its center, then their halos already overlap. They are not separated. They are not islands. They are not isolated. They are already touching at their faint, ragged, outermost edges right now tonight as you listen. Read that again, slowly. The Milky Way and Andromeda are not approaching each other across an empty gap. Their outermost halos are already in contact. They have, in all probability, been in contact for billions of years. The gap, the famous gap, the gap in the diagram in your head, it does not exist. The halos meet somewhere in the middle, and that middle is where these wandering stars live. One of the same astronomers, a researcher named Yuding Feng, said something even more striking. He said that he would not be surprised if there were a few dozen stars right now that were being contested between the two galaxies. Contested, gravitationally claimed by both, not belonging to the Milky Way, not belonging to Andromeda, but pulled simultaneously by both, drifting in a slow gravitational tug-of-war that has been going on for ages, and that will continue going on long after our sun has died. Stop and picture one of those stars for a moment. A single, faint, ancient sun. Probably older than 10 billion years, older than the Earth, older than almost everything you can name, drifting alone in the deep dark with no planets, no companions, no neighbors within hundreds of light years. On one side of it, an enormous spiral. On the other side, another. Both pulling. Both calling, both in some sense claiming it. And the star itself just moving slowly, patiently on an orbit that may never resolve. Not orbiting one galaxy, not orbiting the other, orbiting the both of them, orbiting the entire local group. These stars do not have names. They are too faint, too distant, too numerous. They appear in catalogs only as coordinates and brightness measurements. There may be hundreds of them, there may be thousands. We do not yet know. We do not yet have the tools, but we know they are there. And we know that for every one we have found, there are almost certainly many more we have not. And here is the part that I want you to sit with, because it changes the geometry of everything. The boundary of a galaxy is not a line. It never was. The textbook drew a line because a line fits on a page, but in reality, a galaxy fades. Its disk fades into its halo. Its halo fades into its outer halo. Its outer halo fades into whatever lies beyond. And what lies beyond, in our case, is not emptiness. It is the outer halo of Andromeda fading inward from the other direction. The two galaxies do not end. They taper. And somewhere in the middle, the tapering ends of each one meet and overlap and blend. And from inside that blended region, no one, no astronomer, no spacecraft, no observer could tell you with certainty which galaxy a given star belongs to. This is a strange thought to hold in your mind. We are used to objects with edges. A cup has an edge, a planet has an edge, a house has an edge. Even a person has an edge, more or less, the skin, the boundary between you and the room. But a galaxy does not have an edge in that sense. A galaxy is more like a fog. It is dense in the middle and it thins outward, and the thinning continues for as far as your instruments can see. And when two fogs sit close enough together, they do not stop at some invisible line. They mingle. The Milky Way and Andromeda are mingling. Their outermost edges are mingling. They have been mingling for a long, long time. So when you picture our cosmic neighborhood now, I want you to picture something a little different from the textbook. Picture two enormous, slowly rotating spirals, glowing brightly at their centers. Now picture each one surrounded by a vast, faint, ghostly halo of ancient stars reaching out in every direction. Reaching and reaching until the halos lap against each other in the middle like two great oceans meeting. There is no shore, there is no beach, there is no border. There is only a wide, dim region where one halo becomes the other, and the stars that live in that region drift slowly, contested, claimed by neither side. That is the first crack in the diagram. That is the first thing we pull out of the supposed void. Not a few stars, not a curiosity, but a wholesale rewrite of where the Milky Way is understood to end. And once you accept that, once you let the comfortable idea of the edge dissolve, the rest of what we are about to find becomes easier to see. Because if the Milky Way does not really end where you thought it did, then everything past that imagined edge is also up for revision. The dwarf galaxies that orbit at 500,000 light-years, the streams of gas that arc between Andromeda and Triangulum, the hot, diffuse atmospheres that envelop everything, the dark matter that holds it all together. None of these things violate the new picture. All of them fit it. All of them are, in some way, exactly what you would expect to find, once you accept that galaxies are not islands at all. But all of this began with stars. Stars are what astronomers can see most easily. Stars are what they have been counting and cataloging for centuries. Stars were the first thing they noticed, when they finally looked carefully enough, that did not match the textbook picture. And once they began to look beyond the stars, once they began to study the spaces between them, with new instruments and new wavelengths and new techniques, they began to find that the in-between was not just dotted with wandering suns. It was populated with entire cities of them. That is where we are going next. We are going to leave behind the lonely scattered stars, the contested wanderers, the silent old ones drifting on the tablecloth between the plates. And we are going to visit the small, faint, half-hidden cities of the local group, the dwarf galaxies. Some of them you may have heard of. Most of them you certainly have not. Some were discovered before you were born. Some were discovered this year. Each of them is a small, ancient world of stars in its own right. Sometimes a few million stars, sometimes only a few thousand, and they fill the supposed void in numbers that would have astonished astronomers even 30 years ago. But before we meet them, I want to ask you a question, a real one. If a star is being pulled equally by two galaxies, if it is contested, if it is shared, if neither side can claim it cleanly, which galaxy does it belong to? Or does it belong to neither? Or does it belong instead to something larger than both, to the local group as a whole, to the entire connected structure we are now beginning to see? Tell me what you think in the comments. Because the answer you give is, in many ways, the answer to the whole question we are exploring tonight. Where does one galaxy end? Where does the next one begin? And whether in the end those questions even make sense at all. And so now, with the contested stars drifting quietly behind us, let us push deeper into the gap. Let us go to the first real settlement we will meet between here and Andromeda, a galaxy in its own right. Large enough to glow faintly to the naked eye on a dark night ancient enough to have been forming stars for nearly the entire history of the universe, and close enough to Andromeda that some astronomers no longer agree on whether it is a separate galaxy at all. Its name is Triangulum, and it is only the beginning. If you have ever lived in a small town and then moved to a city, you know the feeling, the strange recalibration of what counts as a place. A handful of houses, a single intersection, a quiet street, these can be a whole world to the people who live there, even though from the highway you might miss them entirely. The local group is a little like that. Andromeda is the city. The Milky Way is the city, and between them, scattered across the supposed emptiness, there are villages, hamlets, outposts, some of them large enough to have their own internal life. Some of them so small and faint that you could pass within a few hundred light years and never know you had crossed through one. The first of these, the largest, the brightest, the one you should know by name even if you have never heard it before, is called Triangulum. Astronomers usually refer to it by its catalog name, Messier 33 or just M33. It is a spiral galaxy like ours, like Andromeda's. It has arms. It has a faint, glowing center. It is forming new stars right now. And it is, by every measure, the third great member of the local group. Triangulum sits about 2.7 million light-years from the Milky Way and only about 750,000 light-years from Andromeda. Pause on that for a moment. From our perspective, Triangulum is roughly the same distance as Andromeda. But from Andromeda's perspective, Triangulum is just down the street. If Andromeda were a dinner plate on the table we built earlier, Triangulum would be a small saucer sitting just a few inches away from it. Close enough that the two have already touched, gravitationally, at least once in the deep past. A close passage, somewhere between 2 and 4 billion years ago, that astronomers can still see written into Andromeda's disk, a flaring of new stars, triggered by the encounter, still glowing today. Triangulum is not large. It contains perhaps 40 billion stars, compared to the Milky Way's 2 or 300 billion, and Andromeda's roughly 1 trillion. But 40 billion is not a small number. 40 billion suns, 40 billion possible solar systems, 40 billion chances. Sitting quietly in what the diagram in your head once called nothing. You can see Triangulum, by the way. On a very dark night, far from cities, with eyes adjusted and patience cultivated, the human eye is just barely capable of catching it. It appears as the faintest of smudges in the constellation it is named for, the small triangle of stars beside Andromeda. Most people who claim to have seen it with the naked eye have probably seen it through wishful thinking, but under truly dark skies, it is there. A trembling, almost imagined glow, the most distant object an ordinary, untrained human eye can perceive, older than civilization, older than agriculture, older than the species that is looking at it. Around Triangulum and around Andromeda and around the Milky Way there are the smaller ones, the dwarf galaxies. And this is where the supposed void really begins to feel populated. Let us start with Andromeda's closest companions. There are two small galaxies you can see, even in a small telescope, sitting right next to Andromeda in the night sky. One is called Messier 32, or M32. It is a compact little ball of stars, gravitationally bound to Andromeda, slowly spiraling in. It looks, in photographs, like a glowing, fuzzy bead pressed against Andromeda's outer disk. The other is called Messier 110. It is larger, more diffuse, a soft, luminous patch off to one side. Together, M32 and M110 are the two most prominent satellites of the Andromeda system. They are old. They are dim compared to their giant parent. And they are slowly being consumed, their stars and gas drawn inward over billions of years. But Andromeda has more than these two. Many more. There is a galaxy called NGC 147. There is another called NGC 185. Both are small, faint, elliptical companions of Andromeda, sitting a few 100,000 light-years to the side. There is one called the Cassiopeia dwarf, also catalogued as Andromeda 7, discovered only in the late 1990s. The brightest and most massive of Andromeda's dwarf spheroidal companions, hidden behind the dust of the Milky Way's own disk, which is why we did not see it for so long. There is one called the Pegasus dwarf, also called Andromeda 6, found in a similar quiet way, by patient astronomers scanning images for things no one had bothered to look at carefully before. There is Andromeda 1, 2, 3, 5, 8, 9, 10, all the way up through numbers in the 30s, Andromeda 32, Andromeda 33, Andromeda 36, the most recent additions to the catalog, discovered just in the past few years. By the most recent count, Andromeda has at least 35 known satellite galaxies, probably more, probably many more, hidden behind the dust of our own Milky Way in regions of the sky that are simply hard to look at. New ones are being found every year. In 2025 alone, astronomers added several. In 2026, just months ago, a galaxy called Andromeda 36 was announced, an ultra-faint dwarf, with perhaps only a few thousand stars, sitting in the outskirts of Andromeda's halo, waiting in the dark for someone with a sensitive enough camera to notice it. And the Milky Way has its own family. You may have heard of the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, two great smudges visible to anyone living in the southern hemisphere, just outside the Milky Way's disk. The Large Magellanic Cloud is, in fact, the largest satellite galaxy of our own, holding billions of stars, currently sweeping past us at about 160,000 light-years away. The Small Magellanic Cloud is its companion, slightly farther, slightly fainter, trailing close behind. Both will eventually be consumed by the Milky Way. Both are already being torn at slowly by our gravity. But beyond the Magellanic Clouds, the Milky Way has a quiet swarm of much smaller companions. The Sagittarius dwarf, which our galaxy has already partly eaten, its stars now scattered across the sky in a long, looping stream. The Canis Major dwarf, which is so close and so disrupted that astronomers still argue about whether it counts as a galaxy at all. The Ursa Minor dwarf, the Draco dwarf, the Carina dwarf, the Sextans dwarf, the Sculptor dwarf, the Fornax dwarf, Leo 1, Leo 2, each one a faint, slow, ancient cluster of stars, orbiting the Milky Way at distances of a few 100,000 light-years. And then, in recent years, a whole new category of discoveries has emerged, the ultra-faint dwarfs. Galaxies so small, so dim, that they contain only a few hundred or a few thousand stars. Galaxies that hide in plain sight, indistinguishable at first glance, from a few stray foreground stars in a deep image. The Milky Way has at least 50 known dwarf companions now. Andromeda has at least 35. Triangulum has a handful of its own. And then, and this is the part that the diagram never showed you, there are the dwarf galaxies that do not belong to any of them. These are the galaxies of the in-between. The ones that drift in the supposed gap between the three giants, gravitationally bound to the local group as a whole, but not closely tied to any single big galaxy. There is one called IC10, a small, intensely star-forming galaxy hidden behind the dust of the Milky Way's plain, near the edge of Andromeda's domain. There is one called the Pisces dwarf, also catalogued as LGS3, sitting between Andromeda and Triangulum. There is one called the Aquarius dwarf. There is one called Leo A, there is one called Sextans A, there is one called Sextans B, there is one called Wolf-Lund-Mark-Mellot, often shortened to WLM, drifting alone at almost 3 million light-years, on the very fringes of the local group. And then, most recently, Pegasus 5, Pegasus 6, Pegasus 7, Pisces 7, Triangulum 3, All of them discovered in the past few years through deep surveys with sensitive cameras designed specifically to find the faintest things in the sky. Some of these recently discovered dwarfs have only a few hundred stars in them. Read that again. A few hundred stars, an entire galaxy, with a name, with a catalog number, with a place on the map. Containing fewer stars than you might see on a clear night from a country road, and yet still bound by gravity, still drifting in formation, still, somehow, a galaxy, by every definition we have. Here is something I want you to picture. Forget for a moment the two great spirals and the gap. Picture, instead, the entire region between them as a slowly turning swarm, Andromeda at one end, the Milky Way at the other, Triangulum hovering near Andromeda. And then in every direction the dwarfs, dozens of them, scattered like sparks around a fire, some close to the giants, some drifting alone, all of them rotating slowly within the same great gravitational bowl. None of them are still. All of them are in motion. Some are falling in, slowly, toward Andromeda or the Milky Way. Some are still on their first long approach. Some, like the Sagittarius dwarf, are already being torn to ribbons, their stars stretched out into vast streams that loop around our galaxy like rings of a smoke. The total number of galaxies in the local group is now believed to be somewhere between 80 and 120. The honest answer is, we do not know. The number keeps changing. Every year, new ones are found. Every year, old candidates are reclassified, sometimes promoted, sometimes demoted. Two of the new dwarfs found near Andromeda in the last few years, Pisces 7 and Pegasus 5, have shown, in careful study, that they may have stopped forming stars about 13 billion years ago. Their star formation was quenched by the heat of the early universe itself, during a period called the epoch of reionization. They are, in some sense, fossils, galaxies that froze in time when the cosmos was barely a billion years old and have been drifting quietly ever since. Older than almost anything else you could point a telescope at. And every one of these galaxies, every dwarf, every ultra-faint, every contested fossil lives in the supposed emptiness. Let that thought rest with you for a moment. Between the Milky Way and Andromeda, in the space the diagram showed as black, there are roughly 100 small worlds. Each one is, in its own right, a galaxy. Each one has its own history, its own collection of stars, its own slow rotation, its own quiet end. Some of them are still being torn apart. Some of them have been waiting, almost unchanged, since the first 100 million years of the universe. Some of them are so faint that no one alive when you were born even knew they existed. And all of them, every single one of them, was left out of the picture you carry in your head. This is the layer of the in-between we can almost see. The layer made of stars, the layer made of galaxies. The hidden cities, the silent outposts, the scattered villages of the local group. But even this is not the whole story. Because once you understand that the supposed gap is full of galaxies, you have to ask the next question: what holds them together? What threads connect them? What feeds them? What flows between them? And here, we are about to descend one more level, below the stars, below the dwarf galaxies, into something more diffuse, more invisible, and almost incomprehensibly more massive than all the stars in the local group put together. Before we go there, though, I want to ask you something. Of all the names I just said, the Cassiopeia dwarf, the Pegasus dwarf, Pisces 7, Pegasus 7, Andromeda 36, Triangulum 3, most of them have never been spoken aloud in any classroom you have ever sat in. They are real, they are out there, they are catalogued, but they live for now only in the papers of astronomers. If you could rename one of these forgotten little galaxies, give it a name that a child might remember, a name that might one day be known the way Andromeda is known, what would you call it, and why? Tell me in the comments. I want to read what you would name them, because somewhere in the next century, when our maps of the local group are more complete, The names we give these places may begin to matter. They may begin to feel like neighbors. And just like neighbors, they do not exist in isolation. They are tied together, not by roads, not by signals, but by something older and quieter and far more vast, by rivers of gas, flowing through the supposed emptiness, connecting Andromeda to Triangulum, drifting around the Milky Way, raining slowly inward from the dark. Rivers we could not see at all until very recently. Rivers that, once we learned to look for them, turned out to be everywhere. It is to those rivers that we will go next. If you have ever stood by a slow river at night, you know that water does not need to be loud to be present. It can move silently in great quantities in the dark, entire tonnages of it sliding past you, while the only thing you hear is the wind. The rivers we are about to find between the Milky Way and Andromeda are like that. They are dark. They are cold. They are invisible to your eye, but they are there and they are vast and they are moving, and they have been moving in some cases since long before the Earth had a surface. The rivers are made of hydrogen. Hydrogen is the simplest thing in the universe. One proton, one electron, sometimes nothing else. It is the oldest element. It is the most abundant element. It is the element from which all the stars are built, and the element that fills the empty places between them. And it turns out, the supposed emptiness between Andromeda and the Milky Way is not really empty. It is, in the simplest possible way, wet. There is gas in it. Cool, neutral, hydrogen gas. Faint enough to escape every telescope for nearly all of human history. Just visible enough, with the right instruments, to begin to reveal a structure that has changed how we understand the in-between. The first river was found, almost by accident, in the 1970s. Astronomers using radio telescopes, which see hydrogen by listening for the faint hum it gives off at a wavelength of 21 centimeters, were mapping the gas around Andromeda when they noticed something odd. There was hydrogen where there should not have been any. A long, thin stream of it, hanging between Andromeda and its companion Triangulum like a faint thread connecting two pearls. They could not explain it. They went back. They mapped it again with better instruments. And there it was, still a true bridge of gas, suspended in the dark, more than 500,000 light-years long, connecting two galaxies that the textbook had said were unrelated. The bridge is real. We have confirmed it many times now, with deeper and deeper observations. It is faint. It is cold. It is sparse. If you flew a spacecraft through it, you would notice nothing, not even on your most sensitive instruments. But integrated across its enormous length, it contains millions of solar masses of hydrogen, drifting slowly between Andromeda and Triangulum. Where the gas comes from is still being argued. Some of it may be primordial, gas left over from the early universe that never collapsed into stars. Some of it may be torn from one galaxy and falling toward the other. Some of it may be the residue of an ancient close encounter, 2 to 4 billion years ago, when Triangulum and Andromeda swept past each other and left behind a thin trail of material in their wake. Whatever its origin, the meaning of the bridge is unmistakable. Andromeda and Triangulum are connected, not metaphorically, literally, physically, by a stream of gas the length of an entire galaxy. The space between them, the so-called void, is bridged by something we can map and weigh and trace. It is not a gap, it is a channel. And the bridge between Andromeda and Triangulum is only the most famous of these structures. Around our own Milky Way, there is something similar but stranger and far longer. It is called the Magellanic Stream. If you live in the southern hemisphere, you may already know its parent galaxies. The large and small Magellanic Clouds, the two great smudges that hang in the southern sky, visible to anyone who looks up on a clear night away from city lights. They are the Milky Way's largest satellites, sweeping past us, drawn into our gravitational embrace. And as they fall inward, our gravity is slowly tearing the gas out of them. The gas does not vanish. It does not disperse. It trails behind the Magellanic Clouds in a long, looping arc that wraps almost halfway around the entire sky. A vast filament of hydrogen, hundreds of thousands of light-years long, glowing only in the radio band, invisible to the naked eye, but absolutely present. Astronomers can map every kink and ripple of it. It is one of the largest single structures in the local group, and it is not alone. There is a smaller stream called the leading arm, which actually runs ahead of the Magellanic Clouds rather than behind them. Gas that was thrown forward by gravitational interactions, falling now toward the Milky Way's disk, raining in slowly from the side. There is the Sagittarius stream, made of stars and gas torn from the Sagittarius dwarf galaxy. The small companion, the Milky Way, is in the slow process of devouring, wrapped around our entire galaxy now in a great looping ring. There are dozens of smaller streams, smaller filaments, smaller cold trails drifting through the halo of our galaxy and out into the in-between, each one a quiet record of an encounter, a meal, a passage, a slow capture. Every one of these streams was, until quite recently, invisible. Every one of them is, even now, faint. But integrated together, the Magellanic Stream, the leading arm, the Sagittarius Stream, the bridge to Triangulum, the dozens of fainter trails, the supposed empty space around and between our galaxies is laced with cool hydrogen, riddled with it, threaded with it, as if a great spider had spent the last several billion years drawing thin strands across the dark. And then, above and around all of these visible threads, there is something even larger, something that took us decades longer to find. Something so faint that we needed a particular trick to see it at all. It is called the circumgalactic medium, the CGM. The cool, ionized gas envelope that surrounds a galaxy, not as a disk, not as a halo, but as a vast diffuse cloud reaching outward, far beyond where the stars are, far beyond where the dwarfs are, far beyond where the textbook said anything existed at all. For most of the 20th century, we could not see the CGM at all. It was too thin, too cold in places, too hot in others. It absorbed almost no light directly. It emitted almost no light directly. It was, for all practical purposes, transparent. And yet it was there, in enormous quantities, surrounding every galaxy we have ever studied. The trick we used to find it, finally, was beautiful. Astronomers realized that if you have a faint envelope of gas around a galaxy, you cannot easily see it from outside. But if there happens to be a distant bright object, a quasar, an active galaxy, a powerful searchlight at the back of the universe, sitting in your sky just behind that envelope, then you can see the gas as a shadow. Not as light, but as the slight darkening of the light passing through it. The gas absorbs specific wavelengths. Each chemical element absorbs its own narrow stripes from the spectrum. And so, if you point a sensitive instrument at a quasar that happens to lie behind Andromeda's halo, the light of that quasar reaches you stamped with the absorption fingerprint of every wisp of gas it has passed through on the way. Astronomers ran a project called AMIGA, short for Absorption Map of Ionized Gas in Andromeda. They used the Hubble Space Telescope spectrograph to look at dozens of distant quasars, somewhere around 40 of them that, by sheer geometric luck, happened to sit on the sky behind Andromeda's halo. They took spectra of each quasar. They studied the faint shadows in the light, and they reconstructed, line of sight by line of sight, a map of Andromeda's gaseous envelope. What they found rewrote the textbook again. Andromeda's circumgalactic medium reaches outward not for tens of thousands of light years, not for 100,000, not for 200,000, but for at least 1,000,000 light years in every direction. Andromeda's gaseous halo, the vast envelope of ionized gas that surrounds it, is more than 1,000,000 light years across. And remember the number we keep returning to. The distance between the Milky Way and Andromeda is 2.5 million light years. If Andromeda's gas halo reaches outward by 1 million light-years, and the Milky Way's gas halo reaches outward by 1 million light-years, and ours does, more or less, by the same recent studies, then their halos are almost certainly overlapping. Andromeda's atmosphere and our atmosphere are touching. I want you to sit with that, not as a fact, not as a number, but as a feeling. The two galaxies are not in separate rooms with a long hallway between them. They are sharing the same atmosphere. There is gas drifting between them right now that belongs to neither, or belongs to both. There is no clean boundary, no gate, no door. There is one continuous gaseous environment, with two dense star-filled regions inside it, and a wide, slowly mixing region between them where the gases of two galaxies are quietly blending into each other. This is not metaphor. This is measurement. We have the spectra. We have the absorption lines. We have, for the first time in human history, a real map. And the gas in this region is not still. It is moving. Some of it is falling inward, toward the galactic disks, on its way to eventually become new stars. Some of it is being pushed outward by supernova explosions, by the violent deaths of massive stars billions of years ago, whose shockwaves are still pressing outward into the halo today. Some of it is being stripped from passing dwarf galaxies, in long thin streams, joining the great cosmic plumbing of the local group. Some of it is being pulled inward from even farther out from the great wider universe, falling into our region along the unseen filaments of the cosmic web. Andromeda is being fed, right now, by gas drifting in from the void. And the gas is, somewhere along its journey, passing through the same region as the gas being pulled toward us. They are mingling. They are exchanging. You see what I mean now when I say that the diagram in your head is a lie of omission. The picture you carry, the picture with the two spirals and the black gap, has erased an entire ecosystem, an entire weather system, a whole quiet plumbing of gas that has been moving between the Milky Way and Andromeda for almost the entire age of the universe. And we have, only in the last few decades, learned to see it. Imagine this for a moment. If you were a tiny observer floating in the space between the two galaxies, you would not see the streams. You would not see the bridge. You would not see the CGM. Your eyes would tell you that you were in absolute darkness, in absolute silence. You would float for 1 billion years and not notice that anything was happening around you. But you would be wrong. Atoms of hydrogen would be drifting past you, slowly, one every few cubic meters perhaps, mostly invisible. You would be inside the largest river in the local group, and you would never know. This is one of the strange consolations of cosmology. The senses we evolved on Earth are exquisitely tuned for the surface of a small, wet planet. They are almost useless for the structure of the universe. The universe does not present itself to us through sight or sound or touch. It presents itself through patience, through instruments, through the slow accumulation of data over generations. And only by that long, patient work have we begun to see what was always there. Filaments, streams, bridges, halos, a wet, breathing, moving cosmos where we once saw only dark. Before we descend further, before we go to the part of the in-between that is hotter still, and thinner still, and stranger still, I want to ask you something. Hydrogen is the most common element in existence. There is more hydrogen between the galaxies than inside them. Almost everything the universe contains is, in some sense, drifting in this thin gas. And most of it, the vast majority of it, is not where you would expect. It is not in stars. It is not in planets. It is not in nebulae. It is out here, in the supposed void, quietly waiting. Does that change how you think about what empty space really is? Did you know, before tonight, that the gaps between galaxies were full of slowly moving rivers of the same element you breathe out 1,000 times a day? Tell me what you think in the comments, because for a long time, the in-between was thought to be a desert, and now we are beginning to suspect it is a sea. And below this sea, thinner than the gas we just described, hotter by orders of magnitude, almost impossible to detect. There is another layer. A layer so diffuse that even calling it gas feels like an exaggeration. A layer at temperatures of 1,000,000, 10,000,000, 20,000,000 degrees. A layer that may hold within it more than a third of all the ordinary matter in the universe, matter that, until just a few years ago, astronomers literally could not find. Matter that was missing. Matter that was lost. Matter that has only now, with new X-ray telescopes scanning the sky, begun to come quietly into view. That is where we are going next, to the invisible weather, to the warm-hot intergalactic medium, to the place where the missing universe was hiding all along. For most of the last century, astronomers had a quiet problem they did not like to talk about at parties. They had counted all the ordinary matter in the universe, all the stars, all the gas in galaxies, all the dust, all the planets, all the cool clouds drifting between the stars, and the number kept coming up wrong. The total mass of all the ordinary matter you can see, in every galaxy across every part of the observable universe, adds up to only a fraction of what the cosmos is supposed to contain. The early universe in the few 100,000 years after the Big Bang left behind a very specific amount of ordinary matter. Protons, neutrons, electrons, the stuff your body is made of. We can calculate that amount precisely from the temperature of the leftover heat of the Big Bang, the faint glow that fills the sky in every direction, called the cosmic microwave background. The numbers do not lie. We know to a high degree of certainty how much ordinary matter the universe was born with. And when astronomers counted up all the ordinary matter they could see, they found, again and again, that more than half of it was missing. Not most of the universe, that is a different problem, a much larger and stranger problem, having to do with dark matter and dark energy. We will come to dark matter shortly. This was a smaller, sharper mystery. The ordinary matter, just the protons and neutrons, the basic atomic ingredients of stars and people, was unaccounted for. Astronomers could find perhaps 40 or 50% of it. The rest had simply vanished from their senses. They called it the missing baryons problem. Baryons in this context is just a technical word for ordinary matter, and the missing baryons hung over the field for decades. Where, in the entire universe, were they hiding? The answer turns out to be right in front of us, drifting in the supposed emptiness, in the in-between. Below the cool hydrogen rivers we walked through in the last section, below the bridges and the streams and the gaseous halos, there is something thinner, something even fainter, something so diffuse that, for most of our history, our instruments could not even detect that it was there. It is called the warm-hot intergalactic medium, the WIM for short, and it is, by current estimates, where most of the missing baryons have been hiding all along. The WIM is hot, not warm in the sense your skin would recognize. Warm in the sense astronomers use when they want to be conservative. The temperatures range from about 100,000 degrees Kelvin to nearly 10 million degrees Kelvin. At those temperatures, every atom in the gas has been stripped of most of its electrons. Hydrogen no longer behaves like hydrogen. It is a soup of bare protons and free electrons, flying past each other at enormous speeds. Heavier elements, what little there is of them, are stripped down to glowing ionic cores. The gas is so energetic that on any human scale, it would vaporize anything it touched. And yet, and this is the part that should make you sit up, the gas is also nearly empty. Pause on this. The WIM is one of the strangest things in the universe, because it is simultaneously among the hottest gas anywhere, and so thin that for any practical purpose, it is a vacuum. A typical density in the WIM is perhaps one particle, one proton, one electron, in a volume of space the size of a small room, maybe a few particles per cubic meter, perhaps fewer. The gas is so spread out that on the scale of a spacecraft, it would simply not exist. You could fly a vessel through the densest part of it and nothing would happen. Your hull would not register a temperature change. Your sensors would read empty space. The atoms are too far apart on average to transfer any meaningful energy to you. The gas is real, and it is hot, and it is everywhere, and you would never know. This is the difference between temperature and warmth. Temperature is how fast the individual particles are moving. Warmth is how much energy gets transferred to your body. In a gas this thin, the particles are racing along at temperatures of millions of degrees, but there are so few of them that, in any given second, almost none of them strike you. The gas is hot. The gas is also, from your point of view, irrelevant. Both things are true at once. The universe is full of strange physics like this, and the whim is among the strangest. Now here is the key. Add it up. Take that ridiculously thin gas and integrate it across the truly vast volumes of the cosmos, across the spaces between galaxies, across the spaces between groups of galaxies, across the great filaments of the cosmic web. And what you find is that this nearly invisible gas, so diffuse that on any local scale it might as well not exist, contains by mass roughly a third of all the ordinary matter in the universe. Some studies push the number higher, closer to 40%. Some push it slightly lower, but by any reasonable accounting, more ordinary matter is sitting in the whim than is locked up in all the stars of all the galaxies put together. Read that sentence again. There is more ordinary matter drifting, almost invisibly, between the galaxies than there is inside them. Every star you have ever seen, every star in every galaxy in every cluster, all of them combined, they are the minority. The majority of ordinary matter has been hiding in the in-between all along. For decades, we suspected this. We could not quite prove it. The whim was so faint, so hot, so spread out, that no instrument could see it well enough to weigh it. We saw faint hints, absorption lines in distant quasars, glimpses of certain ionization states, statistical signals in deep ultraviolet surveys. But a real direct map eluded us. That is changing now. There is a telescope in space called EROSITA, an X-ray instrument launched in 2019, operated by a German-Russian collaboration, designed to scan the entire sky in soft X-rays. X-rays are emitted by gas at exactly the temperatures of the whim, and at the cooler edges of the even hotter atmospheres that surround big galaxies. In its first full sky survey, completed in 2020 and analyzed in detail through 2024 and 2025, EROSITA mapped the warm hot gas atmosphere of the Milky Way itself for the first time. It traced its shape. It measured its temperature. It found that the gas extends outward in vast oblate shells, reaching well beyond the galactic disk, and that its temperature is, by their best fits, somewhere between 1 and 2 million degrees. This is the immediate envelope of the Milky Way, the hot bubble in which our entire galaxy floats. And just like Andromeda's cool gaseous halo extends outward by more than 1,000,000 light-years, the Milky Way's hot halo extends outward over similarly enormous distances. The hot halos of the two galaxies are, almost certainly, also touching. They are mingling. The same way the cool gas of one galaxy mingles with the cool gas of the other, the hot gas does too. There is no clear boundary. The hot atmospheres of the local groups two giants flow into each other, and into the wider warm-hot intergalactic medium beyond, in a continuous, slow, invisible weather system that has been doing what it does for nearly the entire age of the cosmos. I want you to picture this, slowly, layer by layer. You stand in the middle of the Milky Way on the surface of a small, wet planet. Above you, on a clear night, there is the disk of the galaxy itself, a band of stars stretching across the sky. Around that disk, invisibly, is the inner halo of stars. Around that, the outer halo with its scattered ancient suns. Around that, the dwarf galaxies slowly looping. Around that, the cool gaseous envelope, the rivers and streams of hydrogen. And around that, vaster still, the hot diffuse atmosphere, million-degree gas, almost a vacuum, but real, extending outward for more than 1 million light-years. And around that, indistinguishably blending in, the WIM itself, the great warm hot ocean of the cosmos, in which our entire galaxy floats like a leaf in a tide. Andromeda is in the same ocean. Triangulum is in the same ocean. Every dwarf galaxy, every contested star, every river of cool gas, every dust cloud and supernova remnant we have ever named, all of them are floating in the same vast, hot, nearly empty sea. There is no shore. You might be wondering, listening to this in the dark, why we should care about gas so thin that we cannot feel it, so hot that we cannot touch it, so faint that for most of human history we did not even know it existed. The answer is that this gas is the universe. It is most of the ordinary universe by mass. The matter that became you, the matter that became the earth, the matter that became every cell of every creature that has ever lived on this planet. That matter was, for most of the cosmic timeline, drifting in something very much like the WIM. Hot, thin, almost transparent, patient. Waiting. Slowly, over billions of years, a small fraction of it cooled, condensed, fell into the gravitational wells of growing galaxies and became stars. Stars made carbon. Stars made oxygen. Stars made every heavy element you are built from. And then those stars died, scattered their atoms back into the gas, and the cycle began again. Some of those atoms are now in your blood. Most of them are still out there, drifting in the warm, hot dark, waiting for the next chance. The WIM is not just a curiosity of cosmology. It is the reservoir from which everything you know was made. And now, finally, we are beginning to map it. We can see the Milky Way's atmosphere with EROSITA. We can see the local group's wider thermal environment by combining multiple surveys. We can use distant quasars and active galaxies as backlights, the same trick the AMIGA project used for cool gas, to find absorption signatures of the hotter material. Each year, our map of the in-between gets a little more detailed, a little less blank, a little less dark. And every year, the missing baryon problem shrinks a little further, as more and more of the lost ordinary matter is found exactly where the theorists predicted it would be, quietly drifting in the warm hot ocean we used to call empty space. So here is the strange and beautiful summary of where we are now. The thing between the Milky Way and Andromeda is not nothing. It is not a void. It is the warm hot intergalactic medium, and it is not just a layer of the cosmos, it is the cosmos. It is where most of the ordinary matter lives. The galaxies, the stars, the planets, the moons, all of the bright places we have ever pointed a telescope at, are local condensations within the larger, dimmer, hotter sea. We are not islands floating in a void. We are dense little knots in a vast, patient ocean, and the ocean has always been there. We just could not see it. Before we move on, I want to ask you something. For most of our lives, we have been told that the universe is mostly empty. That space is a vacuum, that the gaps between things are nothing. And tonight you are learning, perhaps for the first time, that the gaps are not empty at all. They contain more of the ordinary universe than the bright places do. They are where most of the material that exists is currently sitting. How does that change the feeling for you of looking up at a clear night sky? Does the dark feel different now? Does the space between the stars feel more populated, more present, somehow less lonely? Tell me in the comments, because I think this particular shift from the dark is empty to the dark is where most of everything is, may be one of the gentler revolutions in how a person can come to see the universe. And once you have made that shift, the next one becomes almost easy. Because the warm, hot intergalactic medium, vast as it is still made of ordinary matter. It is still made of the stuff that makes you. But ordinary matter, as we have hinted twice now, is only a small fraction of the total. Around all of this gas, woven through it, holding it, shaping it, pressing it into the long filaments and slow currents we are finally beginning to see, there is something else. Something far more massive. Something we have never seen and may never see directly. Something that, when you finally understand its scale, will change one last time the picture in your head of what lies between the Milky Way and Andromeda. We are going next to the dark. Here is a strange exercise. Stop for a moment and imagine you could see gravity. Not the things gravity acts on. Not the planets, not the stars, not the gas. Just the gravity itself. The pure pull. The invisible pressure that holds the universe in shape. Imagine that you opened your eyes one night and instead of stars, you saw the gravitational field. You saw where mass was concentrated. You saw where it was thin. You saw the wells. You saw the valleys. You saw the long ridges where matter accumulated, and the great hollow regions where it did not. If you could see that, the sky between the Milky Way and Andromeda would not look anything like what your eye normally tells you. It would not be a flat black gap with two bright dots inside it. It would be something far stranger. It would be a great gravitational landscape, with two enormous wells sunk into it, side by side, almost touching at the rim. The wells would be far larger than the bright galaxies. They would extend outward, deep and wide in every direction. They would overlap. And the entire landscape would rest on a slow, patient, almost flat surface, a vast, gently warped sheet, stretching outward for tens of millions of light years before it began to drop off into the much deeper voids beyond. This is the architecture of dark matter. And it is the next layer we have to look at, because all of the things we have walked through tonight, the wandering stars, the dwarf galaxies, the bridges of hydrogen, the warm hot ocean, none of them would be where they are without it. Dark matter is the scaffolding. It is the reason the in-between holds together. It is the reason the local group is a group at all. And it is, by every measurement we have, the dominant kind of matter in the universe, by a factor of about 5 to 1. Let me try to put that number in human terms. For every kilogram of ordinary matter in the cosmos, every kilogram of star, of planet, of person, of gas, of dust, there are approximately 5 kilograms of dark matter. We do not know what those 5 kilograms are made of. We have never directly detected a dark matter particle. We do not have a sample of it on Earth. We have built enormous, exquisitely sensitive detectors deep in mines and tunnels, and they have stood quietly for decades, waiting for a particle to interact with their atoms, and almost nothing has happened. The patient detectors keep watching. The patient theorists keep refining. And dark matter, whatever it is, continues to do its quiet work in the universe, unbothered by our curiosity. We know it is there for 3 reasons. We know it is there because galaxies rotate too fast. The outer stars and their disks orbit at speeds that would tear those galaxies apart, if all the matter we could see were the only matter present. Something invisible is holding them in. We know it is there because galaxy clusters are held together by far more gravity than the visible matter inside them could ever provide. And we know it is there because the cosmic microwave background, that faint glow left over from the early universe, carries within it a precise statistical pattern that only makes sense if most of the matter in the cosmos is the unseen kind. 3 completely independent lines of evidence, all converging on the same conclusion. There is something out there in vast quantities that does not interact with light, but does interact gravitationally. It is real. It just happens to be invisible to every part of the electromagnetic spectrum we can see. So let us return to the Milky Way and Andromeda, and let us look at them now through the eyes of gravity instead of light. The Milky Way's dark matter halo, the great spherical region of dark matter in which our galaxy is embedded, has an estimated mass of around 1 trillion solar masses. The galaxy itself, the disk and the bulge and all of its stars, contains maybe 1/10 of that in ordinary matter. The rest, the great majority, is dark. And the dark halo extends outward not for 100,000 light-years like the textbook disk, not for a couple of 100,000 like the interstellar halo, but for hundreds of thousands of light-years more. Some estimates put the edge of the Milky Way's dark matter halo, its virial radius, the boundary beyond which dark matter is no longer gravitationally bound to us, somewhere between 500,000 and 1 million light-years from the galactic center. Andromeda's dark matter halo is at least as large. Most estimates suggest it is slightly larger, slightly more massive, perhaps closer to 1.5 trillion solar masses. Its virial radius extends, similarly, somewhere between 500,000 and 1 million light-years out into the surrounding space. Add those two numbers together. Now compare them to the distance between the Milky Way and Andromeda, which is 2.5 million light-years. You can do the arithmetic in your head. Two halos, each reaching outward by close to 1 million light-years, in galaxies separated by 2.5 million light-years. They are touching. They are almost certainly overlapping. The dark matter envelopes of the Milky Way and Andromeda are pressed against each other in the middle of the in-between. They have been pressed against each other for the entire history of the universe. There is no real gap, gravitationally speaking. There has never been a real gap. The two galaxies have been part of a single connected dark matter structure since long before the Earth existed. The local group is not a collection of separate islands. It is one large gravitational well with two deep pits sunk into it, and dozens of smaller divots scattered around them. The bright galaxies you see, the bright matter, the stars, the gas, are sitting in those pits. But the pits themselves are joined. This is one of those slow realizations that, once you have it, you cannot let go of. The Milky Way and Andromeda are not approaching each other across an empty space. They are sliding through a shared dark matter landscape that has held them in relation for billions of years. Their gravitational identities are not separate. They never were. They are local features of a single connected thing. But this is not even the full picture. Because in the last few years, simulations of the local universe have shown something even stranger about the architecture our galaxy is embedded in. In 2025 and 2026, a new generation of computer simulations was published, attempting to reproduce the observed motions of every galaxy within 10 megaparsecs of us. That is, every galaxy within about 32 million light-years of the Milky Way. Astronomers fed in everything we currently know about the velocities, the positions, and the distances of the nearby galaxies, and asked the computers to find the distribution of dark matter that would best explain what we see. The simulations ran. The patterns emerged. And what came out the other end was a structure that surprised many of the researchers involved. The local group, it turns out, is sitting on a vast sheet of dark matter, not a halo, not a cluster, a sheet. A great flattened wall of dark matter, stretching outward for at least 32 million light-years in every horizontal direction, but quite thin in the vertical sense, relatively thin, compared to its enormous width. Above this sheet and below it, there are large, deep voids. Empty regions where almost nothing exists. The dark matter has collected, almost everywhere in our region of the universe, into this sheet-like structure, and almost every nearby galaxy, including ours, including Andromeda, including Triangulum, including the entire local group, sits on it like leaves resting on the surface of a still pond. This sheet has a name, more or less. Astronomers call the orientation it traces the supergalactic plane. It is a very old idea, going back to the mid-20th century, when astronomers first noticed that the brightest nearby galaxies were not scattered randomly across the sky, but tended to lie along a single great circle. They called this circle the supergalactic plane, and it was, for decades, treated as a curiosity. Now we understand what it really is. It is the visible signature of the dark matter sheet on which our entire local universe is built. The galaxies lie along the plane because the dark matter lies along the plane. The matter follows the gravity. The light follows the matter. And the architecture, the real architecture, is invisible. Imagine that for a moment. The entire visible neighborhood of our galaxy, every nearby galaxy that we have ever named, every dwarf and giant and irregular within 32 million light-years of us, is sitting on the same great gravitational sheet, like beads of water on a wide, slightly tilted window. The Milky Way is one bead, Andromeda is another. The Maffei galaxies, IC 342, Centaurus A, M81, all of these are beads, some larger, some smaller, all of them clinging to the surface of the same hidden wall. And the voids above and below us are not empty in some accidental way. They are empty because the matter ran downhill into the sheet billions of years ago and never returned. So the in-between is not just full of stars and gas. It is shaped. It is structured. The Milky Way and Andromeda are not floating in random directions in space, on courses set by chance. They are embedded in a great flattened gravitational structure that constrains how they can move, how they can fall together, how they can drift apart. The dark matter sheet decides the future. It always has. And here is a beautiful detail. The simulations, by running the gravitational physics of this sheet forward and backward in time, can explain something that had puzzled cosmologists for a long time: the observed local quiet of the Hubble flow. The universe is expanding. We know this. Galaxies in general are moving away from each other. Distant galaxies are receding from us at speeds that increase with distance, in the famous pattern Hubble discovered a century ago. But in our immediate neighborhood, in the few tens of millions of light-years around us, the expansion is curiously calm. Galaxies are not receding from us with the speed the universal expansion would predict. They are nearly stationary relative to us. Some are even moving toward us. For decades this was a puzzle. Why is our local universe so quiet? And the answer, the simulations show, is the dark matter sheet. The sheet has so much mass, spread over such a large region, that it gravitationally suppresses the expansion in its vicinity. It pulls everything inward. It holds everything in close formation. Our local quiet is not a coincidence. It is the gravitational signature of the structure we are sitting on. The same sheet that gives the supergalactic plane its shape is also gently grasping every nearby galaxy and keeping it from running away with the rest of the cosmos. The Milky Way and Andromeda are not just bound to each other by their own mutual gravity. They are bound together to a much larger gravitational raft on which they have been sailing slowly for the entire history of the universe. Now look back in your mind at what we have built. We have the stars. We have the dwarf galaxies. We have the rivers of hydrogen. We have the warm hot ocean. And now we have the dark matter, the great quiet architecture beneath all of it, the sheet of mass that explains why our neighborhood is shaped the way it is, why the local group hangs together, why the in-between is full of structure rather than chaos. The diagram you grew up with, the diagram with the two spirals and the black gap, has been not just filled in, it has been replaced. The supposed void has become a populated, breathing, gravitationally connected region of the cosmos. The two galaxies have become two density peaks in a single large structure. The line between them has dissolved. And from this perspective, from inside the great shared landscape of dark matter, gas, and small drifting galaxies, there is a question that becomes almost impossible to avoid. We have spent the last 7 sections quietly dismantling the idea of a gap. We have shown that the Milky Way and Andromeda are not really separate. They share stars. They share gas. They share atmospheres. They share an overlapping dark matter halo. They sit on the same great gravitational sheet. So what does it even mean, after all of this, to ask whether they will one day collide? To collide, two things must first be separate. And the closer we look, the more we realize that they may never have been. Before we go to that question, though, the question of the future, the question of the so-called collision, the question that, for more than a decade, was treated as a certainty, and that in 2025 became a coin flip again. I want to ask you something that has been quietly sitting at the back of my mind since we started this section. If two galaxies share a single dark matter halo, if their gravitational footprints overlap, if they sit on the same great sheet and have done so for the entire age of the universe, are they really two galaxies? Or are they one giant structure that we, with our limited vision, see as two bright spots? What would you call something like that? A bound pair, a single binary, a double galaxy? Or do you think the human language for these things just has not caught up yet? Tell me in the comments, because I think how we name these things matters. The words we use shape what we see. And if the two great spirals of our neighborhood are really one connected being, then maybe, one day, we will need a new word for what they are. And whatever they are moving, slowly, patiently, on a course we can now measure with extraordinary precision. Andromeda is sliding through the dark matter sheet in our direction. The Milky Way is sliding through it toward Andromeda. We have known this for a long time. What we have not known, until very recently, is what happens next. And what we have learned in the last 2 years has overturned more than a decade of confident predictions about the future of our galaxy. That is where we are going next, to the dance. To the slow, gravitational, hundreds of millions of years choreography that is unfolding right now between the Milky Way and Andromeda. And to the new study, published in 2025, that turned what was supposed to be an inevitable collision into something far less certain and far more interesting. For more than a decade, if you asked an astronomer what would happen to the Milky Way and Andromeda, you would get a confident answer. The collision was certain. The galaxies were headed toward each other at about 110 kilometers per second, blue-shifted in their light, falling in along a course we had measured carefully with the Hubble Space Telescope. In about 4.5 billion years they would meet. The disks would tear. The stars would scatter. The two great spirals would lose their elegant shape and crash through each other, and through several long, slow passes over the following billion years, they would merge into a single enormous elliptical galaxy. Astronomers gave it a slightly ridiculous name. Milkomeda, Milky Way plus Andromeda. A name half joking, half serious, the way scientists often name things that they expect to be debated forever. The image went everywhere. Documentaries used it. Textbooks used it. Children's astronomy books used it. There is a famous Hubble illustration of how the night sky over Earth will change as Andromeda approaches. First, a small smudge growing larger, then a great companion galaxy looming alongside the Milky Way, then the dramatic close pass, then the long, messy merger. By the time the sun dies, in about 5 billion years, the sky over what was once Earth would be unrecognizable. Our two galaxies, dissolved into one another. The diagram in your head, in some sense, was destined to become wrong even on its own terms. That picture, comfortable and dramatic as it was, has now been challenged. In 2025, a study was published in the journal Nature Astronomy by a group led by Tilsawala at the University of Helsinki, with colleagues from Durham, Toulouse, and Western Australia. The study took everything we know now, every refined measurement from the Gaia Space Telescope, every updated mass estimate for the Milky Way and Andromeda, every careful tracking of the local group's motion that has accumulated in the years since the original 2012 prediction, and asked a simple question. Given everything we now know, and given how uncertain those measurements still are, what are the actual odds of a collision? To answer it, they did something straightforward but enormous. They ran 100,000 simulations of the future. They built a careful model of the gravitational physics. They included not just the Milky Way and Andromeda, but Triangulum and the Large Magellanic Cloud, and the wider local group. They considered 22 different variables, and for each one, they used a range of values consistent with current measurement uncertainties. Then they sampled randomly across that uncertainty space 100,000 times and watched what happened next. The result was a shock. Not just because of what it said about Andromeda, because of what it said about how certain we should have been all along. In the simulations, the probability of a head-on collision in the next 5 billion years, the famous timing of the old prediction turned out to be only about 2%, not the near certainty we had imagined. 2%, a small chance, a long shot. The original confident prediction from 2012 had not been wrong, exactly. It had been one possibility among many, treated as the most likely because the older measurements made it look that way. With better measurements, with the influence of other galaxies properly included, that single scenario certainty fell apart. The overall probability of any merger between the Milky Way and Andromeda in the next 10 billion years, the longer window, allowing for slower, less direct paths, came out to roughly 50%. A coin flip. In half of the simulations, the two galaxies eventually merged. In the other half, they did not. A coin flip. That phrase was used by several of the researchers themselves, till Sawala described the shift as going from a near certainty to a coin flip. The fate of our galaxy, which had been treated for more than a decade as a settled question, became uncertain again, not because the science had failed, because the science had become more honest. The previous studies had given a single answer. The new study gave a probability distribution. And the truth, for now, sits somewhere inside that distribution, waiting to be narrowed down by future data. There are a few specific reasons the answer changed. The most important is the Large Magellanic Cloud, the Milky Way's largest satellite galaxy. The LMC is massive. It is much more massive, by recent estimates, than astronomers thought even 20 years ago. And it does not orbit in the same plane as the Milky Way and Andromeda. Its orbit runs almost perpendicular to that line. As the LMC swings around us, it pulls on the Milky Way. It nudges us. It gives our galaxy a small but persistent gravitational tug, sideways, off the direct course toward Andromeda. In the older predictions, the LMC was either ignored or treated as a small perturbation. In the new simulations, it is a major player. And its perpendicular tug has the statistical effect of pushing the Milky Way slightly off the direct collision course, by a margin large enough that, in roughly half the scenarios, the two galaxies do not pass close enough to merge. They sweep past each other, missing by something like 1 or 2 million light-years, and continue on independent trajectories, at least for the foreseeable cosmological future. There is also a more subtle factor, called dynamical friction. When two galaxies pass close to each other, their dark matter halos drag on one another. The drag bleeds energy out of their orbital motion. If they pass close enough, the drag eventually pulls them into a merger, even if their initial pass would have been a clean miss. But if they pass too far apart, the drag is too weak, and they sail past each other and apart. In the new simulations, the critical distance, the closest approach that would lead to a future merger, is somewhere around 500,000 light-years. If the Milky Way and Andromeda come closer than that on their first pass, they will eventually merge, over the following billions of years, even if the initial encounter is a clean flyby. If they stay farther apart, they may never come back together. The future depends almost entirely on the geometry of that first pass, and that geometry depends on factors we cannot yet measure precisely. So the new picture, the picture we now hold as the most honest assessment of our cosmic future, looks something like this. Right now, Andromeda is approaching us at about 110 kilometers per second. In about 4 billion years, the two galaxies will reach their closest approach. Whether they come close enough to gravitationally lock into a merger, or whether they sweep past at a safe distance, remains genuinely uncertain. In some scenarios, the two galaxies merge in around 8 to 10 billion years. In others, they wave at each other across the dark and continue on their separate orbits within the local group for many billions of years more, perhaps forever. There are three broad outcomes, and I want to walk you through each one slowly, because they each carry their own kind of cosmic weight. In the first scenario, the galaxies miss. Their first close approach is too distant for dynamical friction to slow them down significantly. They pass each other, distort each other gently with their gravity, perhaps swap a few outer stars, perhaps tug at each other's halos, and continue on their separate paths. The sky over what is left of Earth in 5 billion years would be dramatic but not catastrophic. Andromeda would loom enormous, filling a third of the sky, glowing softly. Then, over hundreds of millions of years, it would slowly drift past, growing smaller again. There would be no merger. The Milky Way and Andromeda, after their long flirtation, would remain two galaxies, bruised perhaps but separate. This is roughly the outcome that occurs in something close to half of the new simulations. In the second scenario, the galaxies pass each other at the critical distance, close enough for dynamical friction to work, but not for a head-on collision. They sweep past, with their dark matter halos dragging on each other, bleeding energy out of the orbit. They separate briefly. Then they fall back together. Then they pass again. Each pass brings them closer, until, over the course of perhaps a few billion years more, they spiral into a final merger. The merger produces a single elliptical galaxy, the Milkomeda of old predictions, only delayed and dragged out. The slow death of two spirals over an extended period that stretches well past the lifespan of the Sun. This is the outcome in another large fraction of the simulations. In the third scenario, the rarest one, the two galaxies meet almost head-on. Their disks slice through each other. Their gas clouds collide. New stars erupt by the millions, in great bursts of formation triggered by the violence of the encounter. The two supermassive black holes at the centers, our own Sagittarius A star, and Andromeda's much larger central black hole, fall toward each other and over hundreds of millions of years form a tight binary, then merge in a thunderous release of gravitational waves. The disks tear themselves apart. The spirals dissolve. A new galaxy is born from the wreckage. This is the dramatic outcome, the one every illustration shows, and it now appears to be the least likely, roughly 2% in the new simulations. It is worth saying, plainly, what does not happen in any of these scenarios. Stars do not crash into each other. Solar systems are not shattered by the encounter. The reason is the same reason the diagram in your head was misleading in the first place. Galaxies are mostly empty space, on the scale of their stars. Even in a head-on collision, the stars of the Milky Way and the stars of Andromeda are so far apart, relative to their sizes, that the chance of any two stars meeting is essentially zero. Our Sun, if it still existed in 5 billion years, would not be hit by an Andromedan star. It would simply be carried along, on a new orbit, in a new gravitational landscape. The collision is a collision of galaxies, not a collision of suns. But of course, the Sun will not still exist in 5 billion years, not as it is now. The Sun's main sequence lifetime is about 10 billion years, of which it has used somewhere close to half. By the time Andromeda approaches its closest passage with the Milky Way, the Sun will be entering its red giant phase. The Earth, if it still exists at all, will already have been scorched or swallowed. The slow questions of what we sometimes call deep time tend to humble human concern. The dance of the galaxies is not measured in human lives. It is measured in stellar lifetimes. So why does any of this matter if none of us will be here to see it? It matters, I think, for two reasons. The first is that the universe is not running on a single fixed plot. It is running on probabilities, on geometries, on initial conditions we are still measuring. When the old prediction said the collision was certain, it was telling us about our confidence, not about reality. When the new prediction says the future is a coin flip, it is telling us something more honest, that the cosmos is open, that the future of our galaxy is not yet decided in any sense, that physics requires that the precise unfolding of the next 10 billion years is still being computed by reality itself, one quiet gravitational nudge at a time. The second reason is that to even ask the question, to ask whether two galaxies will collide, requires you to think of them as separate. And here, after everything we have walked through tonight, the question begins to feel almost strange. The Milky Way and Andromeda are already touching at their outer halos. They share an atmosphere. They share a dark matter sheet. They have been mingling stars and gas across the supposed gap for the entire history of the universe. To ask whether they will collide is to ask when a long, slow process, already long underway, will finally arrive at a single visually obvious endpoint. The merger, if it happens, is not the start of their entanglement. It is the conclusion of one that began billions of years ago. I want you to picture this, slowly, one more time. Two galaxies on a great gravitational sheet, embedded in overlapping dark matter halos, sharing a common atmosphere of warm hot gas, threaded together by rivers of hydrogen. Populated between them by 100 small dwarf galaxies and countless wandering stars, drifting closer to each other for the past several billion years on a course that may in some far future bring them physically together, or may instead allow them to sweep past and continue dancing in slow orbit around a common center of mass for many billions of years more. That is the real picture. That is the honest one, not a collision, not a near miss. A continuous, slow, gravitational conversation between two galaxies that have been talking to each other since long before our solar system existed, and that will, in some form, continue talking to each other long after it is gone. So before we move on, I want to ask you something. For more than a decade, every astronomy lover, every documentary viewer, every casual reader of science news has been told the same thing, that the Milky Way and Andromeda are going to collide, no question, in about 4.5 billion years. It was treated as a fact. It was repeated as a fact, and in 2025 it quietly stopped being a fact. The future of our galaxy went from a certainty back to a coin flip. How do you feel about that? Does it bother you that something you thought was settled has been reopened? Does it make the universe feel more uncertain, or in some way more alive? Tell me in the comments. Because I think how you respond to that kind of news, the news that a long-held cosmic certainty has dissolved, says something about how you live with the universe in general. Whether you want closure from it, or whether you are content to let it remain partly unknown. And whether or not the two galaxies eventually merge, the picture we have built tonight remains intact. The in-between is full. The supposed void is populated, gravitationally bound, gaseous, structured, embedded in a great dark matter sheet that holds it in shape. The Milky Way and Andromeda are not two islands considering whether to one day touch. They are two density peaks within a single connected structure, already touching at every layer except the visible one, and even that, in some long-deferred future, may yet dissolve. That structure has a name of a sort. It has neighbors. It belongs to something larger. The local group itself is only one knot in a much greater web, a web of galaxies and gas and dark matter that stretches outward across the entire universe, in long, quiet filaments threading between vast, empty voids. We have come this far without zooming out beyond the local group. But to truly answer what lies between the Milky Way and Andromeda, we have to step back one more time. We have to see the local group in its place. We have to find out what connects us not just to Andromeda but to everything else in the cosmos. That is where we are going next, to the cosmic web, to the great filaments, to the local sheet and Laniakea, and the slow currents in which our entire neighborhood is drifting. We have spent this entire video looking inward, looking into the in-between, layer by layer, peeling back the supposed emptiness to find the stars, the dwarf galaxies, the rivers of gas, the warm hot ocean, the dark matter sheet. And now for the last full section before we close, I want us to do the opposite. I want us to step back, to zoom out, to rise in our imagination above the local group itself, and to see where this whole structure, the Milky Way, Andromeda, Triangulum, all the dwarfs, the entire connected dark matter raft on which they sit, actually lives. Because the local group is not the universe. The local group is a knot, a small bright knot in a much larger thing, and the much larger thing has a name. It is called the cosmic web. Imagine that you could rise slowly above your own galaxy. Up through the disk, past the inner halo, past the outer halo, past the wandering RR Lyrae stars and the contested old ones. Up through the warm-hot atmosphere. Up through the dark matter envelope. Up until the Milky Way is just a dot in the dark below you. Keep rising. Andromeda comes into view off to one side. Triangulum joins it. The dwarf galaxies appear like sparks. The whole local group reveals itself, a connected gravitational island, perhaps 10 million light-years across. Now keep going. If you continue to rise, the local group itself begins to shrink. Other galaxy groups appear in the distance, hundreds of thousands of times farther away than anything we have spoken about tonight. There is a group around the great galaxy Centaurus A, off to one direction. There is a group around the spiral galaxy M81 in another. There is the Sculptor group, the Maffei group, the Canes Venatici cloud. Each of these is a smaller version of our own local group, a few large galaxies, a swarm of dwarfs, a shared dark matter halo, embedded in its own quiet stretch of intergalactic gas. And as you rise still higher, you begin to see the pattern. The galaxy groups are not scattered randomly through space. They are strung along great filaments, long, thin chains of matter, like glowing threads, that twist and branch through the cosmos in every direction. The filaments meet at nodes, where larger collections of galaxies pile up into clusters. Between the filaments lie enormous voids, regions of space hundreds of millions of light-years across, where almost nothing exists. Voids so empty that even the warm, hot intergalactic medium thins out almost to nothing, where you could travel for tens of millions of years and not encounter a single galaxy. This pattern, filaments, nodes, voids, is the cosmic web. It is the largest structure in the universe. It is the shape of the matter distribution on the very largest scales we can map, and our local group sits inside it, as a small bright knot at a relatively quiet location, far from any of the great nodes. The most famous nearby node is the Virgo cluster. It lies about 54 million light-years away, in the direction of the constellation Virgo. Virgo is a true cluster, a vast collection of perhaps 1,000 to 2,000 galaxies, including some genuine giants. It is far larger than our local group. It dominates the gravitational landscape of our part of the cosmic web, and our entire local group is, very slowly, falling toward it, drawn in by its gravity. We will not arrive anytime soon in cosmological terms. The Hubble flow is still strong enough to keep us at a distance, but the pull is there. We are moving. Andromeda and the Milky Way together, drifting at a few hundred kilometers per second in the general direction of Virgo, riding the currents of the cosmic web. Around the Virgo cluster, there is a wider structure called the Virgo supercluster. It includes Virgo itself and a great many smaller galaxy groups, including our local group, as a faint and outlying member. The Virgo supercluster used to be considered our largest cosmic home. For most of the 20th century, this is what astronomers would have said if you had asked them where in the universe we lived. They would have answered, in the Virgo supercluster on the outskirts. That answer changed in 2014. A team of astronomers led by Brent Tully used precise measurements of the velocities of nearby galaxies to map the flow of matter through our region of the cosmos. They asked a different question than anyone had asked before. Instead of trying to define our supercluster by where the galaxies sit, they tried to define it by where the galaxies were flowing. They mapped the gravitational currents. They asked where the matter in our neighborhood was being pulled toward and from where it was being pulled away. What they found was that the Virgo supercluster, as it had been defined, was only a subregion of a much larger flow. The currents of galaxies in our region of the cosmos all converged on a single, vast gravitational center called the Great Attractor, several 100 million light-years away, hidden partly behind the disk of our own Milky Way. The whole region, our local group, the Virgo cluster, several nearby clusters, hundreds of thousands of smaller galaxies, was sliding toward this single shared destination. And the boundary of that flowing region, the watershed of our cosmic neighborhood, defined a supercluster much larger than Virgo. They gave it a name, Laniakea, a Hawaiian word meaning immense heaven. Laniakea is the home address of the Milky Way at the scale of the cosmic web. It contains roughly 100,000 galaxies. It is more than 500 million light-years across. And every galaxy within it, including ours, is gently drifting toward the Great Attractor at the heart of the structure, on currents that have been flowing since the early universe. So the next time you read your address in your head, your name, your street, your city, your country, your planet, your solar system, you can keep going. Your galaxy, your local group, your local sheet, your Virgo supercluster, your Laniakea supercluster, your filament of the cosmic web, your patch of the observable universe, all the way out, layer by layer, until the words begin to fail. But there is one more piece of this picture that matters for our story tonight, because we have to come back now to the question we have been circling. What is the relationship between the local group, the in-between of the Milky Way and Andromeda, and this enormous web? It turns out that the dark matter sheet we walked through in the last section, the great flattened structure that holds the local group in place, is not isolated. It is part of the cosmic web. The sheet extends outward in our region into the local section of the Virgo supercluster. The galaxies along the supergalactic plane, which our two great spirals follow, are tracing the local edge of a vast filament of the cosmic web. The filament feeds into Virgo. Virgo feeds into Laniakea. Laniakea feeds on its own slow timescale toward the next great structures in the web beyond. In other words, the in-between of the Milky Way and Andromeda is not just full at the local level. It is connected, gravitationally, to everything else in the cosmos. The cool hydrogen drifting between us and Andromeda is part of the larger gas distribution of the cosmic web. The dark matter sheet beneath our local group is a tiny portion of the dark matter scaffolding of the universe. The warm-hot intergalactic medium does not stop at the edges of the local group. It continues, thinner and thinner, into the wider filaments, where it is being mapped slowly by the same X-ray telescopes that found the missing baryons in our backyard. There is no gap between the Milky Way and Andromeda. There is also, in some sense, no gap between the local group and the rest of the universe. The cosmic web is one connected structure. The Milky Way is one bright knot in it. Andromeda is the next bright knot, just down the filament. The whole arrangement, from the smallest dwarf galaxy out to the largest supercluster, is bound together by a single continuous landscape of dark matter, gas, and gravity. The cosmos has no walls. It has only different densities of the same connected thing. This is the picture that has emerged from the past 2 decades of cosmology, and it is, I think, one of the most quietly beautiful realizations our species has ever produced. For all of human history, we have looked at the sky and felt like islands. We have imagined the Earth alone, then the solar system alone, then the galaxy alone, then the cluster alone. Each generation has had to give up another layer of solitude. And what has been revealed layer by layer is that we are not anywhere alone. We are embedded. We are connected. We are part of a great patient web, and every quiet drift of matter near us is, at some level, part of the slow currents of the entire cosmos. I want you to hold this in your mind for a moment. The next time you find yourself outside on a clear night looking up, I want you to try something. Do not look at the stars. Do not look at the smudge that is Andromeda if you can find it. Look at the dark instead. Look at the patches of sky that seem empty. Pick one and stare at it. Now imagine beneath that patch of darkness the layers we have walked through tonight. There are scattered old stars drifting between galaxies. There are dwarf galaxies, faint and ancient, slowly orbiting. There are rivers of cool hydrogen threading from one place to another. There is the warm, hot ocean, the great atmosphere of the cosmos, at temperatures of millions of degrees, almost a vacuum but everywhere. There is the dark matter sheet beneath all of it, holding everything in place. There is the cosmic web, branching outward into the great filaments. There are other galaxies, other groups, other clusters, other superclusters, all sitting on the same connected gravitational landscape. You are looking through all of it. Every photon that has ever entered your eye from a dark patch of sky has passed through this entire structure on the way to you. The dark is not empty. It is the deepest part of the picture. It is the part with the most things in it, and the part we are only just beginning to learn to see. Before we close, I want to ask you something. We have spent 2 hours walking slowly, through layer after layer of what lies between our galaxy and the next. We have stripped away the diagram in your head, replaced the island universes of Kant with the connected web of modern cosmology, and reframed the so-called void as a populated, breathing, gravitationally bound region of the cosmos. Looking at it this way, as a web instead of as scattered islands, does this match the picture you carried into this video tonight, or does it overturn it entirely? Did you know that the gaps between galaxies were not just full, but connected, and that the connection runs out through filaments and superclusters, and across the entire visible universe? Tell me in the comments, because how we picture the cosmos shapes how we feel inside it. And I would love to know how the picture in your head has shifted over the slow hours we have spent here together. And now, with the in-between filled in, with the cosmic web sketched, with the great picture as complete as we can make it, there is one last thing to say, one last reframing, one last quiet realization that has been waiting at the end of every layer we have walked through. We have been asking all evening what lies between the Milky Way and Andromeda. We have answered the question layer by layer. Stars, dwarf galaxies, hydrogen, warm hot gas, dark matter, cosmic web. Each layer real, each layer present, each layer filling the supposed void with something measurable, something named, something that belongs to the universe just as much as the bright spirals do. But there is one more thing that needs to be said. One last gentle truth that you may, by now, have already begun to sense. We have been talking all evening about the in-between, and the more we have looked, the more it has become clear. There is no in-between. The word itself was always a kind of mistake, a relic of the diagram, a relic of the idea of islands. And if you have followed me this far, if you have stayed with this slow walk through the layers of our cosmic neighborhood, then you are ready, I think, to hear what comes next. That is where we go now, to the last realization, to the dissolution of the question itself, and to the quietest, simplest, most personal observation we can make before we say good night. So let us look back at the journey one last time before we close. We began with a diagram, a picture you have carried since childhood, Two glowing spirals, a black gap, a number, 2.5 million light-years. Simple, tidy, almost comforting in its emptiness. The kind of image that fits on a single page, that fits in a single thought, that fits in a single line of a textbook. The kind of image that, by leaving everything out, leaves you with the feeling that we are alone, our galaxy alone, our companion alone, the great dark between us, a void that nothing crosses, that nothing fills, that nothing knows. And then slowly we began to take that diagram apart. We went to the wandering stars first, the ancient, faint, contested ones, drifting more than 1 million light-years from any galactic center, claimed by neither galaxy, claimed perhaps by both. The boundary of the Milky Way, we discovered, is not a line. It is a tapering, a fading, a long, quiet thinning that meets, somewhere in the dark, the slow tapering of Andromeda coming from the other side. Two galaxies, no edges, already mingled. We went then to the dwarf galaxies, the hidden cities of the in-between. Triangulum, the third great spiral of our neighborhood. The Cassiopeia dwarf, hidden behind the dust of our own disk. The Pegasus dwarf, the Pisces dwarf IC10, forming new stars in the dark Andromeda 18, Andromeda 36. Pegasus 7, Pisces 7, Triangulum 3. Names that no schoolchild has ever heard, galaxies that no diagram has ever shown, each one a real world of stars, drifting in the supposed emptiness, some of them as old as the universe itself, some discovered only this year. We went deeper. We went to the rivers of cool hydrogen, the bridge between Andromeda and Triangulum, a 500,000 light-year stream of gas connecting two galaxies that the textbook had said were separate. The Magellanic Stream, a great looping arc of hydrogen torn from the small companions of the Milky Way, wrapped almost halfway around our sky, invisible to your eye but real to every radio telescope on Earth. The leading arm, the Sagittarius Stream. The vast cool atmosphere of Andromeda, reaching outward by more than 1 million light-years, blending with our own, mapped only in the last few years by the patient work of catching the light of distant quasars passing through the in-between. And below the cool gas, thinner still, hotter still, we went to the warm-hot intergalactic medium. The great ocean of nearly invisible gas, at temperatures of millions of degrees, so diffuse that any spacecraft could fly through it and feel nothing. And yet, integrated across the vast volumes of the cosmos, containing more ordinary matter than every star in every galaxy combined. The missing baryons found at last, drifting quietly in the supposed void. The hidden majority of the visible universe, sitting in plain sight in the place we used to call empty. And below that, finally, we went to the dark matter, the great quiet architecture beneath everything. The gravitational sheet on which our entire local group rests, like leaves on the surface of a still pond. The overlapping halos of the Milky Way and Andromeda, already touching, already pressed against each other for the entire history of the universe. The supergalactic plane, traced in the light of bright galaxies because it follows, faithfully, the structure of the unseen mass beneath. And then, finally, we rose above the local group itself, and we saw that everything we had walked through was part of something larger, a cosmic web. Filaments stretching across the universe, galaxy groups strung along them like beads on a thread, clusters at the nodes, voids in between. Our local group, one small bright knot in a vast structure that reaches across hundreds of millions of light-years. Laniakea, our cosmic home address, gently drifting toward the great attractor at the heart of our region. The Milky Way and Andromeda, side by side in the same knot, on the same thread, in the same web, in the same continuous fabric of matter that extends as far as our instruments can reach. That is the picture, in all its layers. The picture we have built tonight together over these slow hours. And here at the end is the realization that has been waiting at the end of every layer. There is no in-between. I want to say that again, gently. There is no in-between. The phrase itself was always a small misunderstanding. It was a relic of the diagram, a relic of the metaphor, a relic of Kant's island universes. It was a word we used when we believed that galaxies were separate things, with definite edges, surrounded by empty space. And we now know, with as much certainty as we know anything in this field, that none of that is true. Galaxies do not have definite edges. The space around them is not empty. The Milky Way and Andromeda are not islands. There is nothing between them. There is only one continuous thing, a single connected structure of stars, gas, dark matter, gravity, and slow gravitational currents, with two bright places in it, side by side, and us inside one of them. The question we asked tonight, what lies between the Milky Way and Andromeda, was a real question, and we answered it, layer by layer. But the deeper truth is that the question itself was malformed. To ask what is between two things, you must first believe that they are two. And on every level we have looked at, that belief turns out to be a simplification, a useful simplification. A simplification that fits in a diagram, in a textbook, in a single line of a children's astronomy book. But a simplification, all the same. The Milky Way and Andromeda are not two galaxies with something between them. They are two bright peaks in one continuous structure. And the structure does not begin or end where we think it does. It extends outward into the filaments, into Laniakea, into the cosmic web, into everything else. There is no between because there is no real apart. This is not a sad realization. I want to be careful here. It can sound at first like a kind of dissolution, as if the things we love about the cosmos, its mystery, its distance, its solitude, are being taken away from us. They are not. The distances are real. 2.5 million light-years is still 2.5 million light-years. The vastness is real. The strangeness is real. The patience required to look at the universe honestly is real. What changes, when you let go of the idea of islands, is not the size of the cosmos. It is your place in it. You are not standing on a tiny rock in a tiny galaxy floating alone in an enormous dark void. You are standing on a tiny rock in a tiny galaxy that is one bright peak in a great connected structure, embedded in a sheet of dark matter, washed in the gas of a wider ocean, threaded by streams of hydrogen reaching across to the next bright peak. Gravitationally held by an architecture that runs continuously out through the cosmic web to every other galaxy you have ever heard of. The universe does not have you on an island. The universe has you woven into it. I want you to feel that for a moment. Just for a moment. You are not separate from any of this. The atoms of your body were forged inside stars, scattered into the warm hot gas, drifted through the rivers of hydrogen, fell into a young earth, became water, became cells, became you. The light of distant galaxies you may have seen once on a dark night far from city lights passed through every layer we walked through tonight on its way to your retina. Through the dark matter sheet, through the warm hot ocean, through the cool streams. Through the dwarf galaxy fields, through the contested old stars, through the outer halo of the Milky Way, through Earth's atmosphere, through the lens of your eye into the back of your skull, and there it became a thought about Andromeda. A thought that maybe led you to a video like this tonight. The universe is not a place where things float in voids. It is a place where everything is part of one slow, patient, connected structure, and you are a small piece of it that has somehow become awake. That is the gift of the in-between. It was never empty. It was never a barrier. It was the medium through which everything is connected to everything else. And we, sitting on the surface of a small wet planet on the edge of one spiral looking across to another, we are not separate from the connection. We are inside it. We always were. Before I let you go, there is one last small favor to ask. If this kind of slow walk through the cosmos is something you want to come back to, on other nights when the dark feels close, when you can't sleep, when you need a soft voice to take you somewhere quieter than your own thoughts, A like or a subscribe really helps the channel grow. It costs you a moment. It means a great deal here. And it means that the next time you want a long, slow journey through some part of the universe, you will be able to find your way back. Whether you do or you don't, I am glad you were here tonight. And now, as we close, I want to leave you with a small thought to carry with you, into your sleep or into the rest of your night. The next time you see Andromeda, if you ever do, on some clear dark night in some quiet place, where someone points and says, "That faint smudge there, that is another galaxy," I want you to remember, there is nothing between you and that smudge. There is no gap, there is no empty stretch. There is only a long, slow, populated, connected living structure, and you and that smudge are both inside it. You are looking at a part of yourself. You always were. Let your thoughts drift now. Let your breath slow. Let your shoulders rest. The cosmos is large and old and quiet, and it is not as empty as anyone ever told you. You belong to it. You always have. And it has been holding you gently the whole time you have been wondering what lies beyond the dark. Sleep well under the stars. Good night.